Okay, hey folks, we are going to pick up right where we left off from the particle in a ring problem, and we're going to expand that out to all three dimensions for the particle on a sphere. This will get a little bit complicated, but we can do it. So let's go for it. So here we can see our physical picture. We still have our particle spinning around the phi axis with a constant radius. However, now we're going to allow our rotation axis to pitch in and out of the theta dimension. So if we go back to our classic right-hand rule, right, with our particle on a ring, we're still rotating around in phi, but now we can pitch in and out of theta. So that means we need our third dimension there, z. And for spherical coordinates, we want to go to the Laplacian, to del squared. Because we have constant radius, we can drop out all of our terms with the derivatives in the radius, and we're left with the following: 1 over r squared times, that's a capital lambda squared, so this is a new thing for us. This is called the Legendrian. And that is the result of the spherical coordinate transformation from xyz to r theta phi. So it does get a little complicated. So now putting that together for our full Schrödinger equation, we've got negative h bar squared over, that would be 2m times r squared. But remember, that's just going to become the moment of inertia, h bar squared over 2i, times the Legendrian squared, operating on psi equals e psi. So it doesn't look that bad, but as we will see, this is going to blow up and get quite complicated. So here is everything that we know. I've got the Schrödinger equation here written out with the Legendrian. We're going to take advantage of the separation of variables technique, where my wave function is a product and my energy solution is a sum. To make this a little bit easier on the writing, I'm just going to write this as big theta times big phi. So instead of writing theta and phi of phi. And now we can plug everything in and go for it. So that's going to be negative h bar squared over 2 times the moment of inertia. And I'll bracket all of that off. And now we're going to distribute psi through each of these terms. So that's going to go 1 over sine squared of theta times the second derivative, partial in phi. And now that's going to be of theta phi, right? So just distribute that psi through. So now that's plus 1 over sine of theta, partial of theta of sine of theta, and partial of theta of big theta phi, and all of that equals e times big theta big phi. So now we can do a couple of steps here. So I'm going to multiply my constants through, and I'm also going to pull out any dependencies that I don't need to worry about. So for example, a second derivative of phi, of theta phi, I only have to worry about phi there, right? So I can pull theta out of that expression. So let's go ahead and do that. So that's going to be 1 over sine squared of theta. I can pull out the theta, so times big theta, and now times the operation of the second derivative of phi on phi, right? So now plus 1 over sine of theta, and I'll pull out the phi this time, times big phi, times partial of theta, sine of theta, partial of theta of theta. And now that all equals negative 2ie over h bar squared of big theta phi. So now I'm going to do 2 more algebraic steps. I'm going to divide both sides of the equation by theta phi, and I'm going to multiply everything by sine squared, just to clean up the algebra. So we'll say multiply by sine squared of theta divide by big theta phi. And so now what I end up with is my sine squared of theta cancels, my theta cancels, and I've got 1 over big phi. And now I can just write those as regular old derivatives since I've separated my dependencies. And now that's going to be plus the following. Sine squared of theta over sine of theta is just sine of theta. And the phi and the phi cancel, and I end up with 1 over big theta. So now that's technically, I started writing those as partials, but those will just be regular old d's. So d theta of sine of theta times d theta of theta. And then we can even add this over to the other side to get that into the standard reduced form. Plus 2ie over h bar squared. Remember, we divided by theta phi, so that goes away. And we multiplied by sine squared of theta. And all of that equals 0. Okay, so now I'm ready to separate this thing. So let's do that on the next slide. So separate from theta and, phi and theta. And so let's go for it. So I've got that down here. So let's copy over what I ended up with. So I ended up with 1 over big phi times the second derivative in phi plus sine of theta over big theta times partial of theta. I did it again, not the partial, but just the regular derivative. d theta of sine of theta, d theta of big theta. And then that is plus 2ie over h bar squared sine squared of theta equals 0. Okay, so we recopied what we got. Now let's separate. So the first separation I'm going to make is the following. I can say I've got all of these thetas together, and I've got all the phi's together. So we'll do that. So I've got 1 over phi, second derivative in phi. And technically, we would say all of that equals 0, but that wouldn't really get me anywhere. So I'm going to do the following, which is done out of convenience and kind of trial and error. I'm going to set all of this equal to negative 2ie over h bar squared. And that means I can do the same thing for my phi function, but I also have to set it equal to those same constants. So I'm going to say sine of theta over big theta times d theta of sine theta, d theta of theta, plus 2ie over h bar squared sine squared of theta, all equals negative 2ie over h bar squared. So now these two things are separated, and we can solve them individually. And another reason why we were able to do this, right, is because we remember E technically equals E theta plus E phi. So we'll have that separation here in those energy solutions. So now if we inspect this first dependence on theta, hopefully you might notice this is our particle on a ring. So that is the exact wave function we got for the particle on a ring. So we've already solved it. And we know the solution for that is big theta equals e to the I, or big phi, excuse me, e to the I ml phi, where ml we know is the square root of 2ie over h bar squared and can take on values 0, plus minus 1, plus minus 2, etc. So brilliant. We've already solved that one. Our solution for phi is hard. So we would have to grind through that for quite a while to solve this sucker. So that's a little bit beyond the scope of this course. So at this point, we're going to rely a little bit on the instructor assist. And we're going to go back to our original separation of variables, noting that psi of theta phi equals theta of theta times phi of phi. We have a solution for phi that could get plugged back in. And eventually, if we were to arrive at a solution for theta, we would plug that back in, and we would end up with the following. I'm just going to write the result down directly. That the normalized wave function, so we would come up with some normalization constant that's dependent on theta and phi, multiplied by psi, of course, equals the following function. So it's called the, I pinned it a crazy thing there. It's called the YLMLs, and those depend on theta and phi. And this would be our properly normalized solution in both theta and phi. So this is known as the spherical harmonics. So there are a class of equations that depend on quantum number ML as well as this new quantum number L that, supposedly we don't know about yet. And we will explore the properties of these solutions in the next video. So I'll see you then.